So this is video 2 in a multi-part series on equilibrium. And what we really want to focus on today is something called LeChatelier's principle. And that's a way to kind of qualitatively figure out how the equilibrium is going to shift in a reaction. And at the same time, I'm going to show you some of the quantitative aspects and how you actually do calculations. So just a reminder, once again, when you look at any kind of equation, general reaction A reacting with B makes products C and D, you can set up an equilibrium expression by always putting the products over the reactants, and always raise those products and reactants to the power of whatever their coefficient is in the balanced chemical equation. So the start is always a balanced chemical equation. And also another reminder that something called the reaction quotient, it actually will do the same calculation. You set it up exactly the same, but what it does is it figures out concentrations at that moment. It hasn't necessarily reached equilibrium. It's at any moment in the reaction. That's what the reaction quotient is. And then the last thing is you can always do a conversion from an equilibrium concentration expression to an equilibrium expression that's expressed in terms of partial pressures according to this formula, which basically shows you that if you take the equilibrium constant done by concentration times RT raised to the power of delta N, and what we do in delta N is we're talking about whether the net gaseous molecules in the reactants are different than the net gaseous molecules in the products. And if they're the same, then this becomes 0 and that goes away, that becomes 1. If it's increasing from reactants to products, and that is some number, and if it's less, in other words, there's more gaseous products in the reactants, then this can actually be expressed as a negative number. But you can look at the prior video to understand exactly how that happens. I just want to remind you of this. And by the same token, you would express the reaction quotient. You can do the reaction quotient in terms of pressures instead of concentrations in the same manner. And this gives rise to K. And another reminder again is if K is very large, if the numbers are greater than 1, your reaction tends to go to the right or towards products. And if the K is very small, less than 1, then the reaction tends to go to the left or to reactants. And that's kind of your review from the last video. So now what we're going to do is look at a way to kind of roughly qualitatively look at which way reactions should shift depending on what you've done, based on the relationship between Q and K. So here's the situation. When this reaction, phosphorus trichloride reacts with chlorine to make phosphorus pentachloride, and if you look, the Kc for that is 24 at 20 degrees C. So all these reactions are happening at 20 C. So let's look at a situation where you start off with basically you have the products a little bit low and reactants a little bit high, so consequently when you do the calculation, products divided by reactants, Q is 15. So remember at equilibrium it's going to go to 24. So the question would be, how is this thing going to shift over time such that you now divide products by reactants and get 24? And the answer is if this number divided by this number is actually low, then this number, products needs to increase and reactants needs to decrease. All right, I get that mathematically if I think about that in the equation. Well, then products is increasing, reactants is decreasing. That means the reaction is literally flowing to the right, or as we'd say, or towards products. And you can see as you watch this reaction over time that that's exactly right. Product starts to increase. At that time, the reactants decrease, and they decrease stoichiometrically. And then when you finally get back to equilibrium, now phosphorus pentachloride is increased up to 0.64 molar, and these have decreased each by 0.4 molar. It's 1-to-1 relationship. And when you do the math, you're now at 24, and this is where this reaction will settle in. So a general way to look at that, look, if Q is less than K, then the reaction is going to start moving towards products. Makes sense? Okay, let's go the other direction. In this case, the products are high, or you have a lot of products, and you have very few reactants, when you do the math, it ends up being much larger. So Q is much greater than QC. Mathematically, you could look at that. If this number is too big and I need to make it smaller, then the numerator has to decrease while the denominator is increasing. And oh, okay, I understand that on the reaction. Then the numerator or the products are decreasing while the reactants are increasing. So this reaction is going to flow to the left or back towards reactants. And you can see that's actually what happens as you watch over time. Q starts dropping off, right? Because the phosphorus pentachloride is actually going down, and then this is starting to build up, and consequently when it gets down to where this is dropped from 2 to 1.82 molar, these have both increased, and when you do the calculation, Q is now 24, which is equal to K, so consequently it's at equilibrium. So if Q is greater than K, then the reaction starts moving towards reactants. And just to kind of a quick seat of the pants way to know how to do that is when you're comparing Q to K, think of it this way. Look at this fraction, products over reactants. If this is high, how would I get it down? All right, well, products would decrease and reactants increase. If it was low, I would do the opposite. So that's one way to look at these and kind of make some predictions on what would happen in terms of concentration. There's another way to look at this, and it's called LeChatelier's principle. And he basically looked at this mathematically and kind of re-expressed that in a more qualitative form. And he basically said this: when a chemical system which is at equilibrium experiences a disturbance, it's going to undergo a reaction that will remove that disturbance. So here's kind of it's saying the same thing, it's just saying a little bit differently. So let's take a look at that. Here's an example. You feel too hot. You've gone to Texas, 3 cities here are experiencing some of the hottest days of the year. What would you do to relieve that pressure? Well, you'd move to a place that's cooler. All right, colorful Colorado. So let's think about that from a chemical standpoint. So here's a reaction where we're taking sodium iodide. These are ionic in solution. And you're reacting with chlorine gas. So chlorine gas starts to bubble through here. And it kind of colors the water a little yellow from the chlorine gas. And then you start to make iodide. This is a redox reaction. Remember that chlorine is much more reactive than iodine because it's a small size, so consequently it jerks the electrons off the iodine. Well, that makes that iodine 0, and that is a kind of a brown liquid which is formed, which goes back into solution, and sodium chloride is formed. So now let's think about LeChatelier's principle as we apply this different situations, how this would affect the reaction. Let's say we just throw in Ki. So the thing to think about is, first off, look at the reactants, look at the products, and you can see that basically as I'm adding Ki, the only place it really affects on here is over here. Iodine is iodine the molecule, which is not iodine the ion. But on the reactant side, that's iodine ion. So I'm actually increasing this. So this is building up iodine ion. So LeChatelier would say, well, hey, how could I shift equilibrium to consume the iodine ion that are building up? And he'd say, well, that makes sense because the reactants are building up. I'm going to shift to the right to consume what's building up. So it's going to shift towards products. And if you looked in terms of Q, you could think of it the same way. Look, if the reactants are building up, how's Q going to shift to finally get to the right K? In this case, right, Q is going to be less than K. So in order to adjust that, what it's going to have to do is shift to the right, move towards products, and that's kind of the rule of thumb. Okay, let's look at another situation. Now we're going to add calcium chloride. So think about these. These are calcium ions don't affect anybody in this equilibrium expression. Chloride ions, though, affect the sodium chloride product. I want to remind you again that this is chlorine atoms here, so they're not affected, not the same thing. This is chloride ions, though, so this is affected. So now I'm going to start building up chloride ions. So now let's think about what LeChatelier would say. Hey, if it's building up products, right, I'm going to shift in a way to relieve that. So I'm going to shift to the left to make that go away. That's what LeChatelier would say. Now, if you look in terms of the Q idea, if it was originally at equilibrium and had settled into some sort of equilibrium, and then you start pouring chlorine in there, now all of a sudden Q is going to build up products, right? You're going to get extra products. And so that then makes the Q higher than the K. And as we've already explained, then it's going to shift back towards reactants. So that's kind of the two ways to look at it. You can either do it with the QK relationship, and it'd be good if you know how to do both, or think in terms of LeChatelier. Where's the stress? Stress is on products. How does it relieve it? By moving back towards reactants. All right, here's a third example. Now we're going to add sodium sulfate. So sulfate is not part of this equilibrium expression. When I set this up, there is no sulfate involved, so that's not going to influence anything. But sodium shows up on both sides. In fact, it shows up in a 1-to-1 equivalent on both sides. So we have no way to relieve the stress, as LeChatelier would think about. I'm putting sodium in on the reactant side, I'm putting sodium in on the product side. There's no way to relieve the stress, so the equilibrium won't shift. All right? And the same thing, if the products are building up at the same rate the reactants are building up, then obviously there's no change in Q, consequently, or the change in Q cancels is the way of thinking about it, and consequently there's no change in equilibrium expression. Right, here's another scenario. What if I added I2? All right, where does I2 go? It's not, this is an iodine ion, this is an iodine molecule. So that would end up over here in the product side. Now I'm going to start building up products. It should shift in a way that relieves that, which is back towards reactant. Shift to the left. That's what LeChatelier would say. All right? But on the other hand, if I started thinking about that from the Q point of view, if it was originally at equilibrium, then I start adding I2. Now the Q is heavy on the product side, right? So now Q is greater than K, and it shifts to the left to absorb extra I2 added. All right, final kind of example. This is a kind of extravagant, but it's good, and it introduces you to some different kinds of chemistries. So a French chemist received the Nobel Prize for working with these, they're called cryptans, and basically what they do is they're size selective. And the way he did this is, if you look at these structures, there's it makes a cage, and there's an opening inside this cage that if you were to protonate all these amine groups, all right, they'd be ammonium groups, but these are great for bonding things that are electron rich, right? Because you have this highly positive proton sitting down inside this cavity. And they built this, you could adjust the chain size by how many carbons are in this cryptan structure. And this is built just right, so it's selective only for chloride ions, but I cannot accept an iodide ion because it's too big, so it won't fit inside the cryptan cavity. So consequently, the presence of this in this reaction would selectively start scavenging chloride ions. So now I have a product that is getting consumed. So LeChatelier would say, okay, the stress on is my products are going away, so how is this going to shift to replace, to take that relief? And he would say, well, it'd shift to the right, because that would create more chlorides to make up for the ones going away. And if you looked at it from the Q viewpoint, you would think, okay, my products are going down. Q is now getting smaller than K. So once again, shift to the right. And this is a good example. So here's an example for you to practice. So what we've done is now we have a gas reaction. We've got nitrogen reacting with oxygen to make NO. And as you can guess, this isn't very probable that this is going to happen, because nitrogen and oxygen are very available in just air. So the K is very low, e to the minus 30. But what would happen if you were to take nitrogen gas into this reaction and start pumping it into a closed cylinder where this reaction is taking place? So now basically you're adding more nitrogen to this reaction. In what way would it shift? So right now you stop the video, read this question, think about the situation, and write out your answer based on both LeChatelier's and the Q. So let's see how you did. So if N2 is going up, right? And if you look at your equilibrium expression, here it is. The nitrogen monoxide is the products, it's squared. Nitrogen and oxygen are the reactants, they're on the bottom. So if N2, that's one of the reactants, is going up, LeChatelier would say, well, if this is increasing, then I'm going to shift in a way that makes it go away, and that's to the right. Okay? It's towards products. Now let's look at it this way. If this was going up, right, this is dividing by a larger denominator is going to make the number smaller. So now Q is smaller than K, so it's going to also shift towards products, is another way of describing it. Right, here's another scenario for you to practice. So now what we're going to do is we're going to take the same reaction, but what we're going to do is put a special membrane on the end that will allow NO to permeate out. So that NO is just going to float out of there. Okay? So now the question is, how would that affect the equilibrium? Alright, so think about that situation. NO's leaving. Stop the video and think about how you would answer that. When you're ready to answer, restart the video. Alright, let's see how we did. NOs are going away, right? So let's once again go over and look at what LeChatelier would say. He'd say, okay, NOs are going away, that's one of the products, so it's going to start shifting to the right to make up for the NOs that are going to the away. Or if you look at it from the Q viewpoint, if this is getting smaller, Q is actually going to be less than K, so once again it shifts to the right. Very good. The effect of changing concentration on the equilibrium can be summarized, right? If the concentration of A increases, the system reacts in some way to consume it. All right? If the concentration of B decreases, the system reacts in some way to replace some of it. Only substances that appear in the expression for Q can have an effect, or they have to appear in an unequal way from reactants to products. Remember the sodium example from what was earlier on in the video. And what we're doing here is not changing the K. Assuming that the temperature is constant, we haven't changed the K. Let's see what other effects we can have. What if you were to change the pressure on equilibrium? But before we do that, I'd like for you to understand there's 3 ways to change pressure, and you need to understand how they differentiate. So in the first scenario, basically, you have an open system. And so for what our example today, what we're going to look at is this, where we're taking nitrogen monoxide, we're going to react it with oxygen, and when we react them, there's going to be an equilibrium formed where you start to make nitrogen dioxide, which is a little dark. So you're starting with these clear reactants, you end up with this dark. So this is how you can know whether you're favoring the right or the left, whether it's clear or whether it's dark. But the first thing I'd like for you to understand is, look, there's 2 moles of this reacting with 1 moles of this in the reactants to form 2 moles of this. So there's actually more gaseous reactants than products. The delta N on this is -1. And that's important to understand when you look at these gaseous reactants. So we have all that in mind. If you set up the equilibrium expression in terms of pressure, it'd look like this, where products are squared divided by one of the reactants is squared, has a coefficient of 2. The oxygen is not, it's a coefficient of 1. So now you can put all this together and kind of think this through, but first I want to explain 3 different types of pressure change. So here we go. We're going to just say that this is basically the NO2, that's the dark ball. Okay, we're gonna make the oxygen blue, and then we're gonna basically make the nitrogen monoxide red. We'll just leave it that way, just to kind of keep it clear. So let's just say we ran this in an open vessel, and what happens is the atmosphere in the room changes. That's one way you could change pressure, right? So basically, the pressure just goes up in the room. I haven't changed anything in here. I just basically changed the pressure in the room. That's one scenario. Okay, here's another scenario. Maybe I take an inert gas, so I have a closed off cylinder where this reaction has taken place. I take an inert gas and I pump it in there, and now what I'm going to do is as I open up this gas cylinder, it's going to increase the pressure in here, not because I'm adding any of the reactants or products, but because I'm adding a fourth inert gas to increase the pressure of this whole thing. And then the third scenario that we might be familiar with is, let's now change this closed cylinder to a piston type cylinder, where I have a piston that can change the pressure by changing the volume. And that's different because when you change pressure by changing volume, volume decreases, the pressure increases. All right, so let's look at this first scenario. So it's the same thing. Basically all we're doing is, and here's an example. I've actually put real numbers in here. The partial pressure of NO2 is 4 psi. Partial pressure of NO is 2 psi. Partial pressure of oxygen is 1 psi. The other, i.e. the air out there, is 7 atmospheres. So altogether, you get a total pressure of 14 psi. Okay, that's great. So now what's going to happen is we increase the pressure. And what that would look like is basically the air, there was an increase in pressure, some change in the weather, so it went all the way up to 20 psi, but that didn't affect the partial pressure of every gas we added in there, right? That's Dalton's law of partial pressure. So the total pressure increased, but the partial pressure of each of these would not be affected in that manner. So consequently, when you put these into the equation, whatever you calculate before, which goes into the equilibrium expression, is the same numbers that you put in after. So there is no change in equilibrium whenever things shift, because there's just a change in the lab pressure in an open system. All right? So here's a very similar situation. I just want you to think of it differently. This happens in the lab. You basically set up the same equilibrium. You have the original pressures as before, but it's in a closed cylinder. And now what we're going to do is we're going to pump in argon and just build up the pressure in there. So you can see the similarity here, that basically we took argon at 7 psi, and now we've increased it up to 20 psi. So the total pressure, according to Dalton's law of partial pressures, went from 14 psi up to 27 psi. But once again, when you go to do the calculations, you don't put anything different into the expression, so consequently changes due to outside conditions won't affect the partial pressures of components. All right, so now let's take the third scenario, and this is the unique one. This is the cylinder. Basically the way to think about it, changing pressure by changing volume. All right, so remember what happens in this. Whenever you change pressure by changing volume, the cylinder actually compresses, changes the volume, and the gas pressures actually change. So consequently what you have after the compression is they increased. So in this case I shrunk the volume in half, so consequently the partial pressures all increased by 2. So the partial pressure of nitrogen dioxide went from 4 to 8, nitrogen monoxide went from 2 to 4, and oxygen went from 1 to 2. So now when you do the recalculation, you can see that what happened, that basically, hey, I started off at 4 as the equilibrium pressure concentration, but now once I change the volume, I now have a QP, which is half that. And so consequently, somehow this is going to start reacting in such a way that it's going to, there's going to be a chemistry change so that this goes back to equilibrium 4. All right, so what does that look like? So let's look at this reaction, how that would happen. So here we go, we're up at our Q of 2. We have this at 8, but we know that the Kp for this is actually 4. That's what it wants to work towards, at equilibrium. So what's going to happen over time? Well, you can think of it from LeChatelier's principle and say, well, gosh, what we increase the pressure, so what we got to do is somehow back off the pressure. And according to this, all right, then the way to back off the pressure is go to the right, because there's 3 moles of gas on the left side, on the reactant side. There's 2 moles of gas on the product side. So it's going to start reacting such that it consumes moles of gas, which is to the right. And this is unique to this particular equation because it's actually a delta N of negative. So as you go to the right, you're actually using up gas and dropping the pressure. So if you thought about it from LeChatelier's principle, it would make sense. Hey, if you increase the pressure by, then this is going to react in such a way that it relaxes the pressure. Now this is unique though, because LeChatelier would have predicted with the atmospheric change and also the argon pump-in change, you might have expected the same thing to happen, but it does not happen. So it does in this case though when you do a change in volume. And so you can look down here and see as the experiment goes on, you do start to raise the pressure of NO2 that's formed, the product. The amount of reactants actually starts to drop off according to the stoichiometry, and consequently you start at a Q of 2 and you settle back into the Q of 4, which is equilibrium K, for a delta N minus 1. And in this case, Q was again less than K, and so it did as we expected, it shifted towards products. Changes in pressure affect equilibrium systems containing gaseous components. In other words, you don't really look at changes in pressure affecting things that are solid or liquid, because the compression doesn't change the volume much. But with a gas, if you start to add pressure to a gas by a cylinder method, you actually can change the volume significantly, i.e. you could change the concentration. Adding an inert gas has no effect. By the same token, having pressure changes in the lab shouldn't have an effect. But changing the volume will cause equilibrium to shift. But keep in mind, if the delta N is 0, and that's not an example we looked at, then there's no way that shifting one way or the other would have any effect. So in that case, if the delta N is 0, increasing even by volume won't cause a change. And once again, we're shifting equilibrium, but we are not changing the K. Okay, so here's an example you can practice. Look at this reaction. Now we're reacting nitrogen with oxygen again, forming nitrogen monoxide. We have it in a closed cylinder at 1 liter. And so the idea is, okay, what would happen if we had this settled into equilibrium? K is 1 times 10 to the minus 30. The concentrations are such that they equal 1 times 10 to the minus 30 in the equilibrium expression. Now all of a sudden you quickly just compress this thing by changing the volume in half. It's now half a liter. How would this equilibrium shift in response to that? So look at the problem, think about the situation, and write your answer. When you're done, you can restart the video and check your work. So let's see how you did. First off, the most important thing to notice is if you look in comparison between the reactants and the products, there is no delta N, right? There's 2 moles of gas on this side and there's 2 moles of gas on that side, so consequently delta N is 0. So by changing the volume and hence changing the pressure, you are not able to see a shift because there will be nothing gained by shifting left or right. So the last but not least is, how does temperature affect equilibrium? So let's start with LeChatelier's principle. So we've got this little reaction here, and here's some details. Okay, I've gone ahead and worked this out, and this is a good reminder. Look, if you set up the equilibrium expression, you put the products over the reactants. If the reactants are solid though, there is no expression for reactants, so consequently it's just products that expresses the equilibrium, and consequently this equilibrium by concentration is 7.1 times 10 to the minus 12, i.e. this magnesium hydroxide doesn't dissolve very good back into water, but when it does, it releases heat. And this is a good thing to keep in mind, is when you have a heat of solution that's negative, that means it's kicking off energy when you dissolve it. And if you want to think of from LeChatelier's viewpoint, when you have an energy release, put it as one of the products, and that'll help you think about this. Whenever energy is consumed, put it as one of the reactants. Show you an example of that here in a minute. So now let's put a match to this thing and see what happens. So LeChatelier would say, hey, look, this creates heat as it goes to products, and now the stressor is heat is coming into the system. How can the equilibrium shifter relieve that heat? And the answer would be it would shift back to the left or back towards reactants to consume the heat. Okay, same reaction. Now let's put it in the freezer. What would happen if it came in the presence of cold? Well, LeChatelier would say, wow, it's getting cold. How's this reaction able to shift to make up for the stress? Well, it would flow to the right, generate heat. So let's look at a different kind of reaction. What would happen if you have a heated solution that's actually positive? In other words, in order to make calcium chloride dissolve, you have to add heat to it. So it's endothermic. So now let's think about the same situation. Now we put a match on this. LeChatelier says, wow, the stressors we're adding heat. How can the equilibrium shift to relieve the stress? Well, it's going to shift towards products to consume the heat. And if you did the same reaction in the cold, okay, there's stress is cold. How can the reaction react in order to create heat to counteract the cold? So it's going to shift to the left towards reactants. All makes sense. And once again, the reminder is, hey, if it's an endothermic reaction as evidenced by a positive heated solution, put heat as one of the reactants. That'll help you know how to solve this from LeChatelier's point of view. So the reaction shifts left to create heat. So here's kind of the summary, right? And I'll let you look back through these slides and view this and think this through a little bit. But this is the only factor that affects the value of K. So in this case, we're not actually shifting equilibrium to achieve a new K. We're achieving a new K, and then the equilibrium will adjust accordingly. So we can still use LeChatelier's principle, but now we need to just be thinking about, okay, if it's shifting right, that means the K is increasing. If it's shifting left, now the K is decreasing. And if you want to quantify this, if you literally want to put numbers on this, we use what's called the Van't Hoff Equation. And if you'll look, this is one of the forms that I discuss in the video appendix B. It's about these forms of the equation, and you should really review this. This will be very helpful when you think about the Van't Hoff equation. In this case, R is 8.314 joules per mole K. I want to point out there is a negative sign on here. And also how things correlate. K1 correlates with this temperature, and K2 correlates with T2. That's the setup for this equation. And you can assign whichever T1 and T2 you want, just so long as you keep the temperature associated with the equilibrium constant together. All right, so let's do this. Hey, let's apply this thing. What's the K at minus 20 C? If you know that at 20 C, right, that the equilibrium constant is 7.1 times 10 to the minus 12, what would be the K if you cool it down to minus 20 C? So now we set this up. We use the Van't Hoff equation. We plug and chug, and notice what we do with our numbers. This is just some key points. First off, temperature can't be in Celsius. We need to use Kelvin because it really truly describes molecular motion. So we take plus 20 C is 293 K, and that is correlated, that's T1, so that's correlated with the 7.1 times 10 to the minus 12th equilibrium constant. Look at the heated solution is expressed in kilojoules per mole, so we have to change it to joules so it'll cancel with the R factor. And so you can just take minus 30 kilojoules is minus 30 times 10 to the third joules. So we can make that conversion pretty quickly. But the other key thing is the formula itself has a negative sign in it. But you have to put a negative sign if the heated solution is exothermic. So there's a double negative, so that will become positive, and that's a key there. So long story short, the negative always stays in the expression. If it's exothermic, you put negative in with the heated solution. If it's endothermic, it would come in positive. So now when you have it in this form, you can plug and chug, kind of solve here. And what you'll do is all these numbers can be collected and simplified to 1.947 when you do the math on this. And then you would have the log of K2 over 7.1 e to the minus 12 equals 1.947. How do you get rid of the log? Do the opposite to both sides, is raise them to the base e. All right? and that will make the log go away, and this just falls out with K. Multiply 1.947 times the 7.1 e to the minus 12, and you basically end up with 5 e to the minus 11. So now let's just stop and think about this for a second. Think about it from LeChatelier's viewpoint. All right? What's the K at minus 20? Well, what have you done? You started hot, you went very cold. This is a minus 30 kilojoules, so the energy is one of the products. So if you're getting colder, it's going to shift in a way that's going to make up for that, which means shifts to the right. So consequently, if you think about K should become more positive. That means a shift to the right. And sure enough, I started off at 7 e to the minus 12. It's very small. I end up at 5 e to the minus 11, so it got a factor, i.e. shifting to the right. So that's going to take you a little time to process, but you can view it from LeChatelier's and still be okay. But the other thing to keep in mind is you got to know your heat of solution. Is it endothermic or exothermic? Because that's going to run the show. So you practice. How does an increase in temperature affect the K for each of the following reactions? Long story short, you now have the heat of reaction. You have the kind of an equilibrium expression. The real question is, which way are things going to shift if you increase the temperature of this reaction? So the way to think about it is, this reaction is settled into equilibrium. Then you increase the temperature, in what way should it shift? This one's at equilibrium, you increase the temperature, which way it's going to shift? This one's at equilibrium, increase the temperature, how's it going to shift? And that can all be based on if you know the heat of reaction. In this case, it's exothermic, endothermic, and endothermic. All right, stop your video, take some time, write your answers. When you're ready, you can restart your video and check your work. Okay, let's see how you did. The first one, because it's exothermic, we put the heat as one of the products. Increase in temperature then would mean, okay, I want to consume that heat, so I shift to the left. So that means K will decrease. That's an equilibrium that's shifting to the left with a smaller K. All right, B, because it's actually endothermic, the heat is one of the reactants. So now if you're increasing temperature, how are you going to consume that? Now it's going to shift to the right, so K will increase. The last one should follow the same trend. Shifts to the right, K will increase. And last but not least, let's do a quick practice on the Van't Hoff application. Molecule D2 undergoes a reaction with ordinary. So this is deuterium, which is a form, it's basically deuterated H2. There's an extra neutron in there, is what that means. And so it's still hydrogen, it just has an extra neutron. But it's possible if you mix these guys together, you're going to get this one-to-one mix of deuterium to hydrogen in the new form. The Kp for this by pressure is actually favorable. It's a little slightly greater than 1, and it's actually a little bit endothermic, so it requires a little energy to run. So if we started off at 298 K and we had a Kp of 1.8, calculate the new Kp when you increase the temperature all the way up to 500 K. So you stop your video, walk your way through it. You might think about LeChatelier's first, just so you know which way the Kp should be going. Then set it up in the Van't Hoff equation and solve. Okay, let's see how you did. When you plug and solve, basically you plug in 1.8 for the Kp, so consequently that's K1. So K1 correlates with T1, and then K2, this should correlate with T2. You plug and chug. Remember once again that if you have a heat of reaction that's in kilojoules, you got to turn it to joules, and I always just quickly just times 10 to the third. That's a simple way, and that way it'll cancel properly with the R factor. All right, so there's the expression, plug, chug, and when you get done, you get 1.90. And let's see if this makes sense. Let's walk it through here for a second. Heat of reaction is endothermic, so energy is one of the reactants. So if you're increasing energy, you want to move in such a way that you consume energy. If energy is one of the reactants, it's going to actually flow to the right, so the K should be getting larger. So if you started at Kp at 1.8 and then you ended up at 1.9, that indeed has shifted the equilibrium to the right, or favoring products. So I hope this video has helped you to understand equilibrium a little better, to understand qualitatively how to determine whether things shift to the right or shift to the left, how to actually quantitatively determine how the equilibrium expression K changes with change in temperature according to the Van't Hoff expression. So continue to watch the rest of the videos in this series to fully understand equilibrium.